One a simple scenario, one a high item count scenario, and then another scenario that would be good to configure specific settings for, which would be telemetry systems where the devices are far, far away from you and you have less bandwidth and higher latency than you're typically used to, and perhaps also slower sampling intervals than, say, the typical 1 second or half second or quarter second sample rates that are present in high-speed manufacturing. So we'll talk about a couple other helpful features of the driver, and then we'll summarize the best practices for each scenario. We are going to record the webinar. We're also going to offer the PDF out, a copy of the webinar, so you could use it as a reference tool when you're either integrating systems yourself or when integrating customer systems. So cool. So let's talk about KEPServer. The architecture of our server platform has the server comprised of 4 key parts. The parts that users interact with are called the server administrator, the administration tool. That's the green and black EX icon in the system tray by the clock. The next process is the configuration tool, and that's what people typically think of as KEPServer. That's our configuration environment and the thing that you use to build channels and devices, and the thing that I'll show you in a few minutes. We also have 2 processes that run in the background. They have no user interface and are controlled and managed by the operating system and the 2 UI elements that you see at the beginning of this process list, our admin tool and config tool. Our runtime process is the heart of our communications broker. This is what actually brokers communications. And then we have a separate event log process that receives events from the runtime, shares them with the config tool, and then determines whether or not to write them to disk in the form of single or extended files. That setting is configurable within KEPServer. So the key takeaway here is that KEPServer's platform is really a combination of 4 key processes, 2 of which run behind the scenes and 2 of which users interact with. The admin tool allows you to adjust application level settings, things like manage licensing, manage our OPC UA interface because it deals with server certificates and quite a bit of configuration related to it. You can manage users within the context of KEPServer, so you can control login behavior with the config tool, and then specific server interface login behavior around HTTP and OPC UA. You can manage the event and diagnostic logs. You can configure whether the logs are persist to disk or not. And then finally, the admin tool lets you manage the runtime from a standpoint of stopping it and starting it and reinitializing it. So the admin tool is your key for managing the behavior of the runtime from a standpoint of is it running or not, is it exposing a UA interface, what users does it have, and then also whether or not the runtime is actually brokering data. The config tool, on the other hand, again, this is what people typically think of as KEPServer. This is our configuration environment. So this is much similar to, very similar to a piece of PLC programming software. You can connect the config tool to the runtime. In the analogy of a PLC, you'd connect the programming environment on Windows to the PLC over a network, either a serial network or an Ethernet network. There's a similar analogy here with KEPServer, except that we're making a local connection to the runtime process in the same operating system. But you can connect the config, you can disconnect the config, you can build projects online in real time with the configuration, or you can disconnect the config and build a project offline, and then maybe ingest it into the runtime at a later time. The few different areas of the config tool that would be good to call out, there is the official name for these areas of the tool are the project view on the left. That's where the channels and devices show up, and tags and tag groups. The view selector, which is B, this is the project selection tool. It'll bring you into areas of plugins where you can configure plugins like our IoT gateway and data logger, link tags, and the advanced tags plugin. The detail view, C, on the right, is a multi-purpose view that renders child objects depending on what element you've selected on the left. So right now the simulator object, the channel, is selected on the left, and so I have a view of its children elements, which is device 1. If I clicked on device 1, I would see the child objects, which would be potentially its tags that are related to device 1. So that's the detail view. That shows you details of the object that you've selected on the left. Then the event log view occupies the lower half of the configuration tool, and it is a running log of events that the runtime is producing. The 4 services work together this way. The admin tool connects to the runtime process using a TCP socket, and it can tell the runtime process to start and stop. That's the right-click context menu that you saw earlier on right here. So the admin tool connects to the runtime through TCP, adjust things and give commands to start and stop and reinitialize. The config tool also connects to the runtime process using a TCP socket. And so we can dynamically edit the project that the runtime is brokering. And as an aside, the runtime is always using default.opf. If you take the config tool and say file open a project and then I want to update the runtime with the loaded project, we're copying the contents of the file that you opened to default.opf. And then if your config tool is online and you're making changes, we're editing in real time default.opf. And then you're asked if you want to save changes to the file that you opened. Then the runtime and event log communicate together again using another TCP socket. The runtime is sending event and error information to the event log, which is then the event log is passing that information to the disk in the form of files, or at the same time providing that data to the configuration tool so you can see the running events in the lower half of that tool. And that's the connection there. The config tool displays events from the event log. So just to reiterate, all of these processes are talking together behind the scenes using the local loopback adapter, the local Ethernet adapter built in Windows to allow applications to use Ethernet to exchange information but reside in the same operating system. So we're using TCP sockets to talk between all of these processes, and it creates a sort of single user experience or a single pane of glass for users to use KEPServer without worrying behind the scenes what's happening. Moving on, in the configuration of KEPServer, everything starts with building a channel. And a channel is created in the project view on the left side of KEPServer. And a channel represents a communications path. It allows you to select the driver, meaning the communications protocol, and then the path out of the PC running KEPServer. So the physical connection, whether it's a serial port or an Ethernet adapter. Finally, it also represents something pretty critical. It represents a single communications thread reserved in our runtime process. And threads in KEPServer are processed in parallel. So one could deduce then that all of our channels are processed in parallel, and that would be correct. So we're processing channel work in parallel from channel 1 to channel 2. We're processing, each channel has a dedicated thread, and we're processing those threads in parallel. So effectively, you're communicating in parallel across channels. So related to that, when you have multiple devices below the channel and a client requests data from device 1 and device 2, well, there's only a single thread at the channel, and it's got to talk to two devices at different IP addresses. So it can't do that at the same time. So the single thread moves through each device sequentially. So it looks like this. The channel 1 is communicating to the PLC, obtaining all of the tags that are required for that particular scan rate. And then it's moving on to device number 2 and acquiring all of its tags that it specified to be read at that particular scan rate. And then it's moving back to device 1 and then moving back to device 2. So the key takeaway here is inside of a channel, devices are communicated to sequentially. Which device gets communicated to first? It is not in the order of the devices listed under the channel. It is just in the order at which the items are referenced by the client application themselves. So if you're using an OPC DA client and you issue an add item command within say an index array of 100 data points, the data points that you place at the top of that array are going to be added first, meaning those items at the top of the array could be for device 2. So device 2 will start the scan process, and device 2 will be first, and then we'll go to device 1 and device 2 and device 1. So again, the takeaway is that we've got a single thread at the channel. Channels are communicated to in parallel. Inside of a channel, devices are communicated to sequentially. And which device starts the communication process depends on which items the client adds first. So if you then split the devices across two channels, you guys probably understand what the result would be now. You get devices communicated to in parallel. Rather than sequentially, you could have two simultaneous conversations with these two devices. So you would increase the performance of your reads potentially by a factor of 100%. So again, if the channel represents a communications path, the device is the destination. And to us, the device object is the representation of that thing out in the field. And it's also protocol-specific settings that let us reach the device, meaning it's a unique identifying information, but also settings that allow us to change the dialect of language that we're using with the device. So maybe the protocol allows us configuration options, things like make the request sizes larger, make them smaller, use this function code, don't use that function code. Those things I could refer to just for sake of ease as dialect changes. So the device object represents those protocol-specific settings that allow us to change the nature of that protocol with the device. So it's one part, this is the representation of that thing I'm talking to. The second part is how do I get to the thing, meaning its IP address, if it's an Ethernet device, and a port maybe. And then some protocol-specific settings that allow us to adjust the way we're using that protocol with the device. So typical device options for Allen-Bradley control logics, there are a lot of different kinds of protocol-specific settings that allow us to create very customized dialects for all kinds of different scenarios, and that's what we'll dig into today. Just before we dig into that a little bit more, there's one last object that I wanted to talk about. So in that project view, on the left side, you'll have channels and devices, and then on the right side, you'll see tags if you select one device. So tags in KEPServer are objects that relate to inside of KEPServer. One of those properties is the address. That address is the location of that piece of data in the target device. So that piece of data could be a memory location, like an integer location used in the ladder logic program. It could actually map to raw I/O, meaning digital inputs or digital outputs or analog inputs and outputs. It could be in a control logics device, it could be a primitive, an atomic data unit inside of a structure. So the tag object is the thing, the piece of data that I'm reading from the device, and then when I bring that device inside of KEPServer, or that piece of data inside of KEPServer, I apply more properties to that. So I give it a name, I give it a quality, I assign it a timestamp, and then inside of that object, I have even more properties that are really to the OPC client. Similar to quality and timestamp, there's description properties, there's data type properties. KEPServer exposes a huge number of properties per tag object, and you can optionally make those available for tag browsing by selecting File, Project Properties, OPC DA Settings, and then say Include Tag Properties when a client browses the server. You can also reference the properties directly simply by looking at what properties we file. So if you look in properties, these properties are available for every tag object we have. So if your client wants even more context than value, quality, and timestamp of a given data object, they have these properties they can work with as well. Say you could expose the underlying device address as a property of that tag object. Cool. Okay, so in general, additional resources are available in a large number of mediums. We've got video collections. Our YouTube channel is updated very frequently. We have a huge number of manuals and guides. We have all of the help documentation in KEPServer is created in PDF form as well, and it's available on the web. You don't have to log in. You just go to support and then get access to our manuals. And then we also have a whole resource library of just general purpose resources that might help you out. So with that said, let's have a poll question. So simply put, do you use currently KEPServer EX? And the answers could be yes, no, and it is entirely fine to say I'm not sure. That happens a lot. So if you could, I'm going to go ahead and don't answer into the question pane. I'm going to kick off a poll. And then I'm going to launch the poll. So now you should see the poll on your screen. So of all of those wonderful people that typed answers into their question pane, I apologize. Please, if you could, apply the same answer to the poll. I'll let the poll run for about another 45 seconds before I close it out. Okay, got about maybe 10 seconds left. At 86% of those voted, 87%. All right, let's see if we can get to 90%. Maybe I should add more flashing lights and sounds to the presentation. Okay, cool. So I'll go ahead and close the poll, and let's take a look at the results. I'll share the results with everybody. 87% of folks on the webinar right now use CapServer, 11% do not, and about 2% are not sure. So that's great. We have a large portion of folks who are familiar with and actively using CapServer, and a good smattering of folks who are getting a lot of education about CapServer today. That's great. Okay, cool. So let's talk about Allen-Bradley products specifically. And also, thanks for those asking questions in the question pane. I count actually 5 engineers in the room with me, so we will be getting those questions answered. All right, so CapServer includes a lot of drivers for Allen-Bradley equipment. We have worked with Rockwell for almost the entire run of our company, which is about 20 years. We've been a partner of theirs for a considerable period of time. We have an OEM version of our software, CapServer, that we provide to Rockwell. They use that for communications to all non-Rockwell devices on desktop systems and on panels. In that relationship with Rockwell, we've had a large number of combined customers, and so it's made a lot of business sense for us to develop a large number of Allen-Bradley drivers. It's actually, the Allen-Bradley suite is our top-selling tool within CapServer, year in and year out so far. So we have a huge number of systems that we support with these drivers. The ControlLogix Ethernet and unsolicited drivers, they can support ControlLogix devices, CompactLogix, MicroLogix, Ethernet IP gateways, Net ENI modules. Our Allen-Bradley Ethernet driver can support Ethernet-enabled PLC5s and SLCs. And then we have a huge number of devices supported from all the other drivers as well. And I'll get into that now. So as I mentioned, the ControlLogix Ethernet driver handles the following devices, so quite a bit of them. Pretty much all of the Logix model series. We are also being used to speak with GuardLogix controllers, and we're working on official support for that, so stay tuned. Oh, I just was... Yeah, oh, okay, sorry about that, guys. I think I had the poll showing instead of the presentation. So let me just back up. The only slides you missed were these. So Allen-Bradley products overview, and then a list of the drivers that we support. And I was about to dig into each driver to show you what models are listed. So within the ControlLogix Ethernet driver, we support all of the Logix lines, and I'd mentioned that we're working on official support for GuardLogix. The unsolicited ControlLogix Ethernet driver actually has CapServer turning into a Logix rack from the standpoint of communications, where a Logix 5000 series PLC that can support SIP data table read and writes, which is basically all of them, they can push data to CapServer. They can actually write data to CapServer. So we don't need to go request it from the controller. And then we just need to be available for the controller to push data to us, and that actually allows you to do call-outs either on local systems or remote systems, or it allows you simply to cut down the communication so we can double the performance by simply not having to request the data. We can just get your device to push the data to us, and then it's available twice as fast as it otherwise would be. We support the new Micro series, the Micro 850. We have support for the Micro 810, 830, and 850 when it's serially connected as well. Allen-Bradley Ethernet is an older Ethernet standard. It predates the Logix model series, and it's used for PLC5s, SLCs, what are called hardbook soft PLCs, which is a variant, a software-based variant of the Allen-Bradley devices. And the soft PLCs have 3 models associated with them: Hardbook, Micro, and Smart. So the AV Ethernet protocol is different from the Allen-Bradley ControlLogix Ethernet protocol that we're employing. And this is an older Ethernet standard used for these older model series, and some newer devices that are emulating older models. We have a similar driver in the Allen Bradley unsolicited Ethernet driver to the unsolicited ControlLogix Ethernet driver. Any Allen Bradley PLC that can support PLC2 type commands can write data to KEPServer. The devices themselves don't need to be PLC2s. They can be more modern PLCs. They just need to be capable of using the older PLC2 command format. And again, that can push data to KEPServer. It cuts down our data acquisition time by half. It allows data to be more readily available and also allows you guys to determine when data should be shared specifically, rather than just setting up a sampling interval and hoping that you're always sampling twice as fast as your values change. DF1 is similar to Allen Bradley Ethernet. It supports older models, PLC5s, SLCs. It also, the DF1 protocols also employed across Control Compact MicroLogix using their built-in RS-232 port. It can also support, so DF1 can also be supported by DH Plus devices using the Allen Bradley 1784 U2 DHP converter. And that's a USB-based DF1 to DH Plus converter. So to KEPServer, it's going to look like a serial COM port. To the topology of the system, it's going to be a USB adapter that's plugged in the machine, and then the operating system is going to be running a little serial COM, virtual COM software that's going to make the USB dongle appear like a serial COM port to KEPServer. So we target that with our DF1 driver, and we're good to talk to DH Plus devices. We also have a native DH Plus driver. We support 6 different types of RS-485 boards. So DH Plus requires RS-485, which does not come standard on PCs. So typically you're adding in a PCI-based DH Plus 485 board. We have 6 different boards supported. We only support 6 boards because we actually write the underlying low-level hardware driver for those boards. So we support those boards natively, and to our DH Plus driver, as long as the board is installed and the operating system is rebooted, the OS will present us a PCI board that our software would understand how to use using the DH Plus driver. So you can check out what boards are supported. In practice, I see more often nowadays that the U2 DHP converter is used than a PCI-based RS-485 board, because it's just about the same cost. There's no difference in the driver performance or anything from Kepware. So it really is just it seems like a simpler way to attach to DH Plus devices than to get an RS-485 cable strung up. So to continue, we have a driver for the Bulletin 900 series, and we support a few different models within that. And then we have a support for the 1609 Universal Power Supply Unit. Our support for that is generic, and essentially it's using the SNMP protocol to talk to the UPS. So let's talk about Logix firmware. So we test our drivers with the latest firmware releases, the latest major firmware releases by Rockwell. We support all of the modern firmware versions, everything from 11.26 to the newest 28.011 for the 5000 series and the CompactLogix and ControlLogix within the 5000 series. You can see the other firmware supported. They should be up to date. Most often, just as a side note, most often Logix firmware minor version updates don't impact successful communications with our driver. And then just how to obtain our Allen Bradley drivers. What you're buying are not individual drivers when it comes to the Allen Bradley stuff. We give all of the drivers to you for the cost of a single driver, and we call that a suite. So the suite includes all of the drivers that I listed except for the Bulletin drivers. 2 Allen Bradley Bulletin drivers must be purchased separately. So those are the only 2 AV drivers that do not come within the Allen Bradley driver suite. So how to install KEPServer. So to add the AV suite or the individual AV drivers during a new install, when you're prompted to select the list of, the selectable list of components, you would want to choose that the Allen Bradley suite is fully installed on the system. And depending on if you needed to use the Bulletin or if you bought the Bulletin drivers, you'd enable those as well. And they're activated or installed separately or selected separately for installation in our installer because they come in a separate driver package. So if you need to modify the existing install to add the drivers in, the same type of menu, the selectable component menu, is available to you. When you're prompted for the installation type, you'd select modify, and then you'd be brought to this menu. So resources for assistance regarding general purpose Allen Bradley stuff, online self-service materials are available on our website, and then you can of course contact us. We have, going on 150 people here in Portland, Maine, here to serve, so just give us a call, let us know what question you have, and we'll help you out. Cool, and then lastly we have one more poll question. We actually have two more poll questions, so bear with us. But we'd really like to know, what do you care most about when it comes to using communication software with AV devices? Is it the speed of performance? Is it reliability, the thing can't break? Is it I need it cheap or I need it inexpensive? Is it that you're willing to take, slower performance if the vendor has validated officially with the vendor of the software is validated with the device vendor? Or do you care about other features like tag generation and redundancy that the communication software might offer you? So I'll go ahead and offer that poll question out, and we'll launch the poll. So I'll leave this open for about a minute. About half the way through the poll. I like to leave it open for another 20 seconds or so. About 75% of the people have voted. So I guess if you had to choose one, what do you care most about? I know some folks would like to say multiple because they have the same desirability, let's say, but if somebody forced you to pick one, really when you think about it, what would that be? We got just another 10 seconds. All right. So I'll go ahead and close the poll and then launch the results. By and large, it was pretty clear most folks care about reliability. So the takeaway for this is that of all other things being equal, if the performance of one solution is not as reliable, if a highly performing solution is not as reliable as a slightly lower performing solution, reliability takes priority. And that makes sense. That's oftentimes what we see. When it comes to reliability, it's oftentimes as important as performance, save for the fact that you really need the thing to be running, and you're okay sometimes if performance suffers just a little bit occasionally. But either way, thank you for taking that poll. It's an interesting feedback for us. I'm going to go ahead and hide the poll and continue on with the presentation. Okay, so right now I just wanted to go through a quick demonstration of using the ControlLogix Ethernet driver inside of KEPServer. So what I'll do, I'm going to create a brand new project here and start from the ground up, and then I'll jump back into the scenarios when we come to them. So here is KEPServer. I've got my configuration tool up and my runtime is running. I want to go ahead and click to add a channel. And again, a channel represents the communications path and the language that we're using. So in this case, it'll be, network interface card number 1, and the protocol will be Ethernet IP. You can name the channels anything you want to give context to the data objects that you're reading from them. I'll go ahead and choose the Allen Bradley ControlLogix Ethernet driver. Let me actually first introduce you to the device I'll be talking with. It's an L63. A ControlLogix L63 that we have in our lab. And so before I actually build the channel in KEPServer, I want to make sure that the device is available for me. So I want to ping its IP address. Good, it's responding to me within 15 milliseconds or so. That's great. Looks like performance is pretty good. So I know that it's up and ready. So now I'll go ahead and go back into KEPServer. The device is up. I just need to build the connectivity to it. So I'll choose the ControlLogix Ethernet driver. I'll go ahead and enable diagnostics. I'll choose the path out of the PC that's running KEPServer. So if I look at my list of available network adapters, I see that my wireless adapter is at 288.18.168. So that's the one that I want to use in order to talk to my device lab downstairs. A setting of default will allow me to go to the operating system and say, hey, give me the first network adapter in your binding order. So if you wanted to check out the binding order, if you do intend to leave this as default, jump into Network and Sharing Center, change adapter settings, and then hit Alt. And you'll be given an actual file menu. If you don't hit Alt, the file menu goes away. If you hit Alt, the file menu shows up, and then you can say Advanced and Advanced Settings. And then this is the list of connections in the order that they will be handed to applications that request the default adapter. So if I look at mine, my first is the my first list is an internal tool here used by our company. The second is my wireless adapter. So I just want to go ahead and assign it the wireless adapter. And I can move through some non-essential screens here. You're safe to leave this as default. Again, this is just a review of establishing simple connectivity. So now that the channel's created, my path is created, I've got a thread ready to go talk, I need to create the device object. So I'll just leave the name as device 1, and the model is a ControlLogix device. And so I want to type in its IP address. And then in the device ID for Logix devices are a combination of the IP address to the Ethernet port or Ethernet module, the port that the module is using to get access to the Logix backplane, and then on the backplane what slot number the CPU resides. So the port to the backplane is always 1. It isn't an Ethernet port. This is a physical hardware port proprietary to Alvin Bradley, but we're going in an Ethernet module, and then we're asking the module to go through its port onto its rack and then go to the CPU, and it happens to be in slot 0. So the device ID for this device is IP address, 1, 0, where IP address is the module, 1 is the port to the backplane, and 0 is the slot number of the CPU. Again, I can leave some of these screens as default. For simple connectivity, you can just go ahead and leave most everything here as default. These are some protocol-specific settings that change our dialect, but I'm not going to dig into those yet. I'm just going to build simple connectivity. Again, more protocol-specific settings that change dialect. Settings around tag database import. I'll show you that and use that in a second. And then I'm done. So the key parts of this are done, and I'm actually ready to start reading data. So with the ControlLogix driver, the protocol affords us the ability to interrogate the device to see its tag database, what users have created as tags using RSLogix. So I can kick off that process by going into device properties and say database creation, auto create. And now if I take a look at the diagnostic menu, this is the conversation that we had with the controller to return its list of tags. And then when I get that list, KEPServer internally reviews the project, parses it out, and then creates the appropriate number of KEPServer tags to match the structures and things that were created in the RSLogix program. So now if I expand the device object, I can see I have a global folder and a test2 tag, and then I have a ton of tags below. And I think I returned about I returned structures that ended us up in creating about 90,000 data points inside of KEPServer. So I can go ahead and start reading those. I'll just launch the Quick Client. When the Quick Client is launched from the config tool, it runs a script to reference every single tag object available inside of KEPServer. So right now I'm going to be adding about 90,000 items and then kicking off KEPServer to read those items. So here's the underlying correspondence with the device, and then here are the data objects. So there we go. Cool. So that's a simple example of building connectivity with the ControlLogix driver. So let's get into a little bit more complicated designs. So first off, the scenario one, I more or less demonstrated this with you, but I'll review this in a little bit more context too. So the simple scenario would be a connection with low tag item counts, really hundreds of items, not thousands of items, or a few thousand items, not 90,000 items. We've got a high-speed Ethernet connection to the ControlLogix device. We're using, let's say in a simple scenario, we're using a gigabit Ethernet network, and we're not doing anything with bandwidth-constricted networks. A gigabit is what we're working with. We decide to import the tag project directly from the controller, and then that allows us to pretty easily get performance testing and benchmarking done. So I'll demonstrate that scenario where we have really simple data needs. The key takeaway is that for a really simple example like this, right, you can leave our settings as default. There isn't really a need to go in and change a lot of our underlying protocol-specific settings that adjust how KEP-server behaves with the device. For hundreds of items, the options around tuning performance are really not going to have that much of a direct impact on the system. So really the takeaway would be if you're dealing with a controller that's connected over a gigabit network that has a few thousand or a few hundred items, you can have a really simple, easy time of connecting to that thing with KEP-server. And the only thing that you really have to enter within KEP-server is this, the device ID, and then you go to database configuration or database creation. Go ahead and click auto create, and then we'll get the tag list back, and then you start reading it, and you're happy day. You don't have to do anything special. Again, and that would be if you connected over a gigabit Ethernet network and you got a few hundred or a few thousand items to return, there's not going to be that great an advantage of you going in and tuning the system for the best performance possible, because you're going to be getting the best performance that you possibly can with that system, really, with its default settings. I'll go into a couple of scenarios that, with the high item count and telemetry example, that might kind of change your opinion about that. If you have a lot of structures that you're reading back and not just the individual elements of the structures, there's a setting here that will allow us to return a whole block, or we'll return the whole structure with a single read versus reading the individual elements, and that would be a performance advantage. But again, with a few hundred or a few thousand items, your sample rate could effectively be around 10 milliseconds, and you'd be probably highly probable to reach that sample rate. So there isn't a great need to go in and adjust things away from the default settings when you're just dealing with the simple scenario of I've got a few hundred or a few thousand items connected in a ControlLogix device over a gigabit Ethernet network, where the default settings should allow you to meet your performance requirements without any adjustments. So that's a simple scenario. Let me then jump into a more complicated scenario where we have high item counts. So we've got 10,000 items. Let's say we have a system with tens of thousands of items. Like my device, it has 90,000 items. That's kind of a lot, for a single device. Not the largest controller project I've seen by any stretch of the imagination, but not an insignificantly sized controller. The scenario would be we've got thousands of items and we've got some multiple devices. We've got an Ethernet, gigabit connection to ControlLogix, CompactLogix, and MicroLogix. We've got different protocol modes that we need to employ, different SIP connection sizes, and different blocking optimizations. So the high item count scenarios, we first really want to tackle them using the strategy of, number one, make multiple connections to the controller to parallelize the tag requests across that device. So where I have, right now I have my high-speed example connection to that ControlLogix device. This might not allow me to return all 90,000 items in the time frame that I need them to be returned. So the ControlLogix devices can support many, many parallel simultaneous connections, and we can leverage those connections. So we can say, you know what, okay, I have high-speed example connection 1 in my channel. Let me take that tag group, actually let me take that channel, copy it, and paste it to duplicate it. And now I've got two connections to the same device. And now what I want to do is remove tags here, and then remove half of the tags here. And so my tag load is split across both channels. So now I am asking for two tag sets across those two channels at the same time. So my performance could be as much as 100% increased. Then you could also make a third connection and a fourth connection, and a fifth connection, and a sixth connection for very, very, very large tag sets. We generally see performance improvements start to stop beyond 6 connections, but it is very much dependent on the controller itself. So it could be that standing up 8 connections, you're able to get each you're able to get 8 times the performance that you otherwise would, or 100% increase every time, all the way up to 8. But generally, we see about 6 connections, and then we don't see performance improvements so much beyond that. But parallelizing your tag set across multiple channels, so that a quarter of the tags are here, quarter here, quarter here, quarter here, that by and large is going to get you the biggest performance improvement when you're dealing with controllers of high tag counts, more than anything else. Now, the second thing that I'd recommend folks do are adjust more of the protocol-specific settings that can change the dialect of communication with the controller. So the first things that we'd want to do is take a look at the timing settings. With this device, we expect for it to get back to us really quickly, because it's on a gigabit network, because it's high speed. So we don't really want to wait very long if we're sending a message and not receiving it. We're better off, and we don't want to waste time, we're better off waiting a very short period of time and re-requesting. Because the only opportunity for the thing to not answer us would be likely if the packets didn't arrive. And in that case, the thing is never going to answer us. And so if you set this to its default, which is 1 second, we're burning time. Sorry, that should be 3. We're burning time waiting a second for that message to come back to us when we know it's just never going to come back, because the only opportunity for the thing not to answer us across a closed high-speed network would maybe be considerable packet loss, electromagnetic interference or something, or the data is just not going to get back to us. So don't wait a long time for the data to come back. It's good to program KEPServer with the expectation that this thing is going to be getting back to you quickly, and so you should only wait a small period of time, and then if you don't hear from it, re-request it. And so we'd re-request very rapidly, and therefore increase performance in the event that we do not receive responses back from your controller. So there's that modification to make. And then in each of the connections, these would be made. And then I'd go into logics options. And I would make a decision about whether to use logical blocking or logical non-blocking. And logical non-blocking is appropriate if you have a very low number of structures in the logics device and you're reading what amount to individual tags, or if you have structures in the logics device and you want to read only a few elements of each one. This is going to return, logical non-blocking is going to return it's going to be issuing reads for the explicit individual, where on the contrary, if you have a lot of structures and you need all of the data in a lot of those structures, then we're better off making a request to the structure and then servicing the reads off of the structure than we are reading each individual element of that structure with an explicit request, because it's just going to burn processor time. It's going to take more time. So with large blocks, you want to use logical blocking so that we request a large group of data back and then service the individual element reads from that. So let's say in this particular controller, I do have a lot of structures, and I am interested in all of the elements of those structures. So I am better off making one request to each structure rather than making one request to each element of the structure. So that can offer me considerable performance improvements. Lastly, the controller is a modern controller where its Ethernet module can support the connection size of 4,000 bytes. So this allows us to create potentially a response message that is up to 4,000 bytes in size, where other models of controller, the default connection size is only 500. So we're able to get 8 times the message size by exposing this particular parameter. And this is available on certain device types, more modern device types, and what device types that are listed out in our help file support connection size of 4,000. We list all that there. The array block size, I saw someone mention that. Yes, you'd want to increase, if you have arrays of data, structures, if you're reading arrays, and you have large arrays, make sure that we're set to read the largest array size possible, and that would be 3840 elements. Okay. So with that, those are really the settings to be mindful of. Number one, make multiple connections to the controller and split the tag load across. Number two, program KEPServer with the understanding that that thing will be getting back to you very quickly, and if it doesn't get back to you quickly, it probably isn't going to be getting back to you at all. So don't spend time waiting to re-request it. Under Logix options, go into logical blocking mode if you are interested in reading large structures back and you want elements inside of those structures. Go into non-blocking mode, which is our default, if you have few structures or if you only want individual elements of structures and only few of them per structure. And then under Logix COM settings, when you can, use the largest connection size possible, and use the, if you're reading arrays, use the largest array block size possible. Cool. So that is high speed. Telemetry is very similar in nature, save for we essentially want to do the opposite of that configuration. We adjust almost all of the same settings, but we actually do it in the reverse way. And so let me jump into that in a moment.
Yeah, just a quick question on the high-speed scenario. So writing a large amount of data to the controller, how is that? How does the server handle that? How does it prioritize that sort of thing?
Sure. So the best write performance would be if you write arrays, right? Because then we can move a ton of data down to the controller at once. The driver itself employs a multi-request message. The driver itself employs a multi-request message so that multiple writes can be delivered to the controller. By and large, though, KEPServer sequentially processes writes. So if you need to make sure that data is moved to the controller in one write message, use an array. You have to write an array, otherwise there isn't going to be the guarantee, unless you write sequentially from your client, that those write messages would be delivered sequentially to the controller. So if it's sequential in nature, make sure that you're writing sequentially. If you just want to move a large amount of data from KEPServer to the device, write an array, because that will be guaranteed that we would move all of that large amount of data at once. If you don't care about it occurring at once, then just issue a bunch of writes to KEPServer. We'll work out which write happens first or second. You shouldn't necessarily need to worry about that, and then the data will get there. But the key is, if you want all the data to get there, and you have a lot of data, if you want all the data to get there at the same time, write an array. Now, what some customers do is, if they have both a highly read-intensive operation and a highly write-intensive operation, they actually create one connection just for writing. So they have maybe 4 or 6 channels for reading, and then one channel just to deliver writes. So that allows the writes to be delivered simultaneously with the reads. Otherwise, we're not going to be issuing 2 commands of different types at the same time. So we leverage our write optimization settings to figure out, what do we do? If we're reading a bunch of stuff and we have a bunch of reads on the queue, what do we do with writes? They always take priority over the reads, but if you end up writing a ton of stuff, that can starve the system from being able to issue reads. So to be able to get reads happening at the same time that writes are happening, we'd advise a second channel to be used, and a separate tag collection be there just for writing data, and then the other tag collection serviced by the other channels there for reading data. So telemetry, so scenario 3 is a telemetry system where really devices are connected through high latency, low bandwidth, energy conserving, or shared mediums, and that they incur, financial costs of passing data, and all of those factors generally force slower and more complicated sampling schedules. So simply put, physical distance increases latency, and we have to accommodate that, amongst the host of other factors in designing these. So physical distances increase latency. Communication mediums that span distances are often expensive and latent. Many RTU-type devices are designed to conserve power and disable comms periodically. And then shared or leased connections can charge per data, whether it's a byte or kilobyte or megabyte or megabit. So you want to be careful about not doing too much over that line and really using the line for exactly the amount of data you want to request and nothing more, nothing less. So to design that, there are a lot of features in the driver, and many of the features by default and many of the features through manual configuration can increase performance. However, not in every situation. So the main consideration here is that you know how our default protocol mode is logical non-blocking? And logical protocol modes ingest the controller's project before we start reading data, so that when we send messages through the controller, we send a very tiny unique identifier. And we're conducting the lookup of a big long tag name to unique identifier, and then sending the unique identifier to the controller. The problem, though, for telemetry systems is that we have to ingest that controller project before we start issuing reads. And we can only maintain, that controller project is only maintained during the duration of connection we have with the controller. Guess what the maximum connection time is? It's 2 minutes of inactivity. So if your sample rate for the telemetry system is once every 5 minutes, we have to destroy the memory controller project upload after every set of reads and then re-ingest it every time we want to issue a read. So a logical protocol mode is not suited for telemetry. So logical and physical modes are much faster per message transaction than symbolic mode, but they require controller project upload on connection and after controller project modification. So if you change the project in the field, it tells us that the project has changed, and our driver knows how to go back and get the copy of the project again to consume those changes. So there's a lot of back and forth. There's a lot of data that has to be ingested before reads occur. And the size of the controller project can potentially be hundreds of megabytes. So every single 5-minute interval, you're pulling back like 100 megs of data that you don't necessarily need to, just to get a faster individual read performance that isn't going to be useful to you. So let's demonstrate that a little bit. I'll go into this configuration of the telemetry system. So here's my telemetry example, and I've got 2 controllers. Now in this case, the controllers need to be communicated to sequentially because the telemetry system really doesn't handle 2 simultaneous requests well. This is my example I'm creating. So we want to build less parallelism in the project in CepServer. So in that case, it actually, instead of creating 1 channel per device, I want to do the inverse. I want to create 1 channel and then put multiple devices on that channel so I can make sure that things happen sequentially. So from there, I want to adjust these settings to first go to symbolic mode. Symbolic mode passes the full ASCII tag name to the controller. And it's a larger message than our logical modes. However, we don't have to ingest the project before we read it. So if you have a 5-minute sample interval, guess what? We can only maintain a connection with the controller for a maximum of 128 seconds without doing anything with it. And then Rockwell says we have to give the controller the connection back. So if your reads are every 5 minutes and we have to destroy the connection every 2 minutes, this is why in a logical mode we're reading back the memory table every time at the start of that 5-minute sample interval, pulling back potentially hundreds of megs of data just to be able to do reads that you don't really need the additional performance for. So for telemetry systems that are latent, that are not local, connected over high speed, we would absolutely recommend using a symbolic mode. It is going to greatly reduce the amount of data you have to ingest over that network before reads are issued. And instead, you're sending more messages, more data per read request, but the total will be most likely very much less than the size of the project that you upload. So from there, I want to tell CepServer about the profile, the behavior of this device, and how long it might take to reply. So it's far away from me. So instead of only giving it 1,000 milliseconds by default, I want to give it 10 seconds or more, and acknowledge the fact that I can't tell CepServer to expect a response back from the device, say for potentially up to 10 seconds after we send a request. And then what we'd want to do is fail after 2 successive attempts. So essentially try and then retry once and then move on to the second controller, because we don't want to spend a lot of time dealing with an unresponsive controller, potentially because the controller, if it doesn't respond to us, there may be some considerable problems in the network at that time, that or maybe a problem with the device itself, where we're better off just trying twice with the same message and then moving on to the second device, and then seeing if we can talk with the second device. rather than continually try to spin our wheels on the first device and just have it fail. Given the nature of the telemetry system, there's so much latency involved, there's so many variables that, if we try twice, it's a pretty high probability of it not working the third time either, so just move on. Additionally, we inject a quarter-second delay between each message, just to slow down communications out of KEPServer to better play with your potential modem systems, where they need a little bit of time to change directions from transmit to receive or receive to transmit. KEPServer has a tendency to be very fast in issuing the next request after getting a response, and sometimes that is too quick for the modems in the telemetry environment in between us and the device. So injecting this quarter-second delay just allows all the systems in between to kind of settle down a little bit before we start using them again. Finally, auto-demotion is important in this scenario because with two devices on the same channel, if I get a failure for this device, and I've pinned the system to be the kind of system where if the device fails one time, it's probably going to fail for a period of time. It's not just a random occurrence, a transient issue. It's going to fail and not be available for a bit of time. Well, after I've retried twice, I can have auto-demotion automatically stop talking to that device for 20 seconds. And so this is device 1. This would mean that if I fail twice to receive a message waiting 20 seconds, I'm just going to go ahead and stop talking to the device for 20 seconds. Just give the network time to settle out. I'll spend my time on device 2, wait for device 1 to come back, and then I'll try after that 20-second demotion period to hit device 1 again. So in situations where if devices become unresponsive and it's transient, and the best scenario is just don't talk with them for a little bit of time, let them do what they do, and then try again to get back to them later. Auto demotion and then these quick failing timing settings means that you're only wasting 20 seconds of time attempting to talk to the controller. And then if 20 seconds of time waiting to talk fails, you're just not going to talk to it for another 20 seconds. And this is adjustable, and then the fail after attempts are successive failure adjustable as well. Finally, Logix COM parameters. This is kind of up to you. If you have a controller in a telemetry system that can support 4,000 bytes, then the question is, how does the telemetry system like that large message size? Is it the kind of system that likes a very large message and can provide a high degree of integrity in providing that large message back to the thing that asked for it? Or is the telemetry system of the design where it'd be better off to ask for a higher number of smaller messages to be delivered? Generally speaking, I find that it's better not to have all your eggs in one basket, meaning don't use very, very, very large connection sizes. Don't make your packets very large because you're more susceptible to loss. But it's a happy medium between the increased overhead of TCP, acknowledging the receipt of all those bytes, the increased message overhead from the additional messages used because we can't create a large message size. It's just sort of a happy medium between large message size that are more susceptible to loss and a higher degree of overhead because of the increased number of messages we have to pass to get the same data. And then that same applies to array block size, and by absolutely we want to, this depends on your sample rate, we want to make sure that we're holding the connection with the Logix device open for absolutely as long as possible, which is 128 seconds. So only if you're sampling slower than 128 seconds are we having to reform our connection and incur more overhead with the controller. So that's a pile of info, but luckily we have it all written down in PDF format. Here are all of the scenario or the optimizations that we went through in the telemetry section. We also lastly have there's two other things I wanted to point out. I want to read the string length automatically because that's an additional read that you may not need. If you don't read the string length automatically, we can either just read the maximum length of the string, or you can write in the LEN tag what length we should return. But automatically reading a string length forces us to make another additional read to the controller when it's in a telemetry system that might not be valuable to you and you might be having to pay for it. Additionally, don't build the project by generating tags online from the device because you're just going to have to pay for the number of bytes that we're using to transit those tag objects across the network. It'd be better in that case to grab the controller project from the programmer and then import the project using that file. So instead of the Logix database, choosing from a device, you choose create a tag database from import file, and we support L5K or L5X. Cool. And then lastly, you could consider using our scheduler plugin, which is a SCADA polling management solution. And so what that allows you to do is, instead of just using a simple interval scanning, it allows you to be very definitive of when KEPServer polls and when it does not poll. So the scheduler can be used to provide specific periods of recurrences and specific exception periods. So we can definitively control when the devices are hit. And even if you have a client coming in requesting data at a quarter second, making explicit reads to tags and doing all kinds of wacky behavior that make the telemetry system unstable, you can block all of that random behavior from occurring and force KEPServer to be in complete control over when that device is communicated with. So that is the last thoughts for the telemetry system. Again, symbolic mode to avoid controller project uploads. Keep tag names short because that'll allow us to transit less data on tag requests. So don't make very long cryptic names in the RSLogix project. Realize that every character you add is going to increase the number of bytes that we have to pass in order to get that tag back. Use arrays. I didn't mention this, but consider the unsolicited driver because you could have the Logix device at the remote site write data back to KEPServer when it needs to, and then you don't have to pull that device at all. You can just wait for the device to push data to us. Don't read string length automatically. Don't import tag objects over from the device. Do it from the file instead. Multiple SIP connections to the same controller, in this case, are probably not going to offer performance gains large enough to offset the increase in messaging. So just because you can create multiple connections to the controller, if it's a telemetry system, you probably don't want to do it because the amount of data you're increased, or the increased messaging is probably offsetting any performance gains you're getting. Yeah, and then finally the scheduler. Consider the scheduler for managing all polling within KEPServer so that you can definitively decide when the device gets hit and when it doesn't. Cool. So last feature is we had one last poll question. I'll go ahead and kick that off. Just I'll leave it running. I know we're a little bit short on time. I'll leave it running for only about 20 seconds.
So while it's running, Sam, here's some interesting questions coming through. So for very low bandwidth channels, like a 9600 baud radio modem polling, are there other protocols like DF1 that would potentially be a better choice? Yeah, it is. It's a simpler protocol. It's a much simpler protocol, and it has less overhead. It still would run over TCP, so you still have the TCP overhead most likely, although you could run it over UDP, but I wouldn't recommend that. So you'd have the increased TCP messaging, but there's a lot of application level chatter that is not present in DF1 that is present in Ethernet IP, capital E, capital N from Rockwell. So yeah, if the system can support it and you can get all the data back that you want, DF1 would be a great fit for remote sites, again, because the application level protocol is less chatty. It passes less data to get the same amount of information back. The only problem is that you don't have context when you're working with DF1. Like all you get to work with is N7:0. You know, instead of a beautiful tag name that comes back from the controller and looks, you know, and describes exactly what it is. So the integration can take some more time with DF1 than it can with Ethernet IP, but it could be in certain situations a much better fit for remote sites. That's a great idea. Great. And then some questions on the unsolicited driver. After you close the poll, someone was requesting for you to demo that if possible, just setting it up. And then someone is asking about the unsolicited driver. What about writes? Like,
oh yeah, sure. Yeah, use a message instruction. Exactly. So I think we actually include. I believe that we include a little write-up in our install directory for the ControlLogix unsolicited driver. Let me see. One sec. Oh yeah, okay, well we may not have that write-up. I have the write-up. It's a Word doc that I can send over to you. But yeah, you use a message instruction. Specifically, it is a SIP data table write, a DT write message instruction. So it's this one right here.
So
Oh yeah, sorry. Yeah, if you close the poll. I'll share the results real quick. Performance improvements 1. So yeah, that message instruction is again, it is a SIP data table. It's a SIP data table write.
Great. And then did you want to just quickly show them, like just create an unsolicited channel?
Oh, sure, yeah. Yep, absolutely. So with KEP-Server, after the message instruction is programmed in the device, you'd create a new channel because you're using effectively what amounts to a new language for us in the context of KEP-Server. So let's say this is Logix unsolicited. Great. I'll choose the unsolicited or slave Ethernet driver. I'll choose a network adapter that I'm listening on. I'll choose the port that I'm listening on. This is the standard Ethernet IP port, 44818. And now I create the device. So this device represents the rack. And then the path from the Ethernet IP module means the path from the module. Is it a local path, meaning 0, or is it a remote path, meaning is it slot 1 or slot 2 or slot 3 or slot 4? So this is the path that you would add in your message instruction in ladder. Go right to path IP address : port number. Now, when we create tag objects in this driver, what we do is use a CSV file in the system here. So you take this native tag database file, and then you're actually creating tag objects inside of inside of this file for your Logix device to target. So if they wanted to write tag 1, when they issue the message instruction to write to tag 1, the tag 1 is present in this file, and we've pre-created a data object for it. So I'll show you that process. So let's say I create, instead of this would be tag SAM1. I'll go ahead and save that. Cool. And now in KEP-Server, I can say, you know what, go ahead and import that native tag database. And in this case, you could place the CSV file wherever you want. We just have a template in our install directory for you to use. Great. I'll go ahead and click Apply and OK. And then here we go. So there's tag SAM1. And then here's the structure that was created, and here are the member elements of the structure. And here's an array tag. Here are the array elements of that structure. So that builds the tags in KEP-Server, and then the message instructions target the controller module, and then target the tag object names. So that's how that works. And we have a Word doc. If anybody is unfamiliar about using message instructions for Logix devices, I can shoot over a document that our driver developer wrote up when we were quality testing the driver. So you could write into sales and request that, or write to me directly if you have my information.
Fantastic.
Great.
All right, well, I think that is pretty much it as far as questions. So thank you, Sam. That was great.
No problem.
There's one or two of you on the line where your question would definitely be better fit for a discussion with our sales application engineers. So we'll follow up with you afterwards and have them contact you directly. Thank you so much for joining this webinar. Let us know via email if you have any further questions. And you will be receiving a recording of this webinar and the PDF of the slides within a couple days of this broadcast. So thank you so much, and enjoy the rest of your day.